Welcome everyone to Energy Systems in the Environment, Leaks, Losses, and Lessons Learned. This is the third in a series of energy system webinar from the Energy Systems Signature Area at the University of Alberta. The Energy Systems webinar series has multiple sessions, and each of the seminars builds on topics of the previous sessions to give participants a more complete picture of energy systems and our current transition to a low hydrocarbon future. We will emphasize a multidisciplinary approach, focusing on technologies and processes, environmental and societal impacts, and their mitigation, ethical considerations, and how energy systems integrate into our daily lives. This series is designed to help guide your awareness of the complex web of technologies, politics, economics, and environmental and social considerations that affect the energy transition. My name is Dan Alessi. I'm a faculty member in the Department of Earth and Atmospheric Sciences at the University of Alberta. And my research group focuses on understanding the water cycle and industrial processes that include hydraulic fracturing, the extraction of resources such as lithium from unconventional sources for use in renewable energy storage, as well as the surface chemistry of materials in the environment. My pronouns are he and him, as you can see in my Zoom name. And if you haven't already, I invite you to add your pronouns to your Zoom name as well. We'd like to begin our FES webinar by respectfully acknowledging that the University of Alberta is located on Treaty 6 territory, a traditional gathering place for diverse Indigenous peoples that include the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. As we explore energy systems, we acknowledge the territories, communities, and peoples that have been essential partners in the research. We are truly grateful to have the opportunity to work, to study, and live on this land. As I said, today is our third session. We'll be learning about the environmental impacts of energy systems, and this includes the development of energy resources, both conventional and renewable. They come with environmental costs, and we will explore those impacts, ways to mitigate or remediate environmental damage, as well as tools to assess the impacts over the life cycle of a particular energy system. To help answer these questions today, we have four esteemed speakers that come from the University of Alberta, Natural Resources Canada, and the University of Calgary to walk us through the different steps along this pathway, showing us how each step influences our society's relationship with energy and how understanding the entire pathway is essential to our energy transition. And so I'd like to list the speakers briefly here. They are Dr. Scott Chang, who's a professor in the Department of Renewable Resources here at the University of Alberta. Dr. Amalesh Dhar, who's a research associate also of the Department of Renewable Resources at the University of Alberta. The third speaker will be Dr. Degenhardt. She is a research scientist in the Ecosystem Health Science Program at Natural Resources Canada. She also serves as an adjunct professor at the University of Alberta. And finally, the fourth speaker will be Dr. Sylvia Sleep, who serves as an assistant professor in the Department of Civil Engineering at the University of Calgary. The format is that each speaker will begin with a 15-minute presentation that will be uninterrupted. After the end of these four presentations, we will open the panel to audience questions. Now, throughout this process, you can submit your questions through the Q&A box on the Zoom, and we'd encourage you to do that at any point during these four 15-minute talks. Please include the name of the speakers that you are directing your question to so that we can direct it to that person. The Zoom chat is also available for you to discuss amongst yourselves, share any thoughts you might have, or ask about the technical challenges. Finally, an important point, please be sure to stick around to the end of this webinar to take our survey. And the survey is aimed at understanding what you might like to see offered in a future webinar series. The information will also be used to help us develop an energy systems curriculum. So this program you're listening to today is developed by the Curriculum Committee of Future Energy Systems. We encourage you also to sign up for future webinars. Past, present, and future webinars will be posted on the Future Energy Systems YouTube channel, as well as the Energy Systems Signature Area website as soon as they are available. So with that introduction, I'd like to start with Dr. Scott Chang with a brief biography. He's, as I said, a professor in the Department of Renewable Resources here at the University of Alberta. He received his PhD in forest soils from the University of British Columbia, and his main interests are in forest soils, biogeochemistry, and the application of soil science and land reclamation, agricultural forestry, and global change. And among his research projects currently is the study and production of biochars and hydrochars. So these are novel carbon-based materials that are effective for the removal of toxic metals and other contaminants from water. And Professor Chang today is going to discuss the topic of conventional energy systems. So I will pass the baton to him. Welcome, Dr. Chang.
Great, thank you. All right. Thank you, Dan, for this introduction and also for inviting me to give this presentation today. This is actually the first time doing such a presentation, so I'm really happy to be able to share some of my thoughts on the impact of conventional energy systems on the environment. And I also would like to thank my co-author, Christopher Zadegwu, for his contribution to this presentation. So first of all, I would like to really quickly define what do I mean by conventional energy. I'm referring to the non-renewable energy resources, including natural gas, coal, oil, uranium, which obviously is a resource that's going to be used for producing nuclear energy, and any electricity from non-renewables. So I think the last point is also really important because we typically think that when we have electrical cars, we are driving electrical cars, we are using renewable energy, which not necessarily is the case. Okay, so that all depends on where the electricity is coming from or how the electricity is being produced. And secondly, my presentation in terms of the impact on the environment, I'm going to be covering the soil, the water, the air, and the water. So I'm going to present a few of my thoughts on each of those environmental components or ecosystem components individually in that order. And then at the end, I'll try to pull them together as well. So the first one is about the impact of conventional energy systems on the soil or on the landscape. And really obviously, and I'm sure you have seen many pictures like this before, that a lot of the conventional energy systems will cause a huge surface soil disturbance. Like this one, this is taken from the oil sands, and the data on this graph is also based on the oil sands as well. So a huge area could be disturbed if the conventional energy resource is being mined through surface mining. And as a result of that, large areas would need to be reclaimed. And so this figure again shows that a lot of surface area disturbance. And currently, again, just using the oil sands as an example, currently a really small fraction of the disturbed area has been reclaimed or certified in particularly. Okay, so a lot more disturbance that needs to be dealt with. So this is obviously a really large impact of some of these conventional energy systems to the environment. The second one is what we are also familiar with is that through the exploration for the conventional energy, a lot of linear disturbance would have been created. So in Alberta, for example, we have more than 1.8 million kilometers of seismic lines that's been distributed across the province. And this picture shows these seismic lines on a really nice aerial photo, a close-up of example of a seismic line disturbance. And this one is a 2-hectare of wooded land had been raised by explosion. This is in the northern Alberta that happened in 2009. And so those are really obvious disturbance that's being caused to the soil, to the ecosystem. But there are some hidden influences or hidden impact of these disturbance regimes on the ecosystem, on the soil. In this case, this is based on some work by Maria Struck. She used to be with the University of Calgary. I think she moved back to the east. I forgot which university she went to. But their recent work indicates that even in these seismic lines, this is more looking at a wetland type of ecosystem, where the disturbance by removing the canopy, changing the thermal condition of the soil, changing the hydrology, raising the water table would increase the methane emissions. And this obviously, as you all know, that this is a fairly potent greenhouse gas. And so those are some of the impacts that could be caused by the exploration of conventional energy in this country. This is an article published a few years ago by David Schindler's group, and they were looking at the oil sands mining and its influence on the loss of wetlands and soil carbon. Loss of wetlands would be fairly obvious, but we may often forget that the loss of wetlands would also mean loss of soil carbon and the loss of the wetland function, where it would be sequestering carbon. But when we lose these wetlands, the sequestration carbon function would also be lost. Moving on to talk about the environmental impact in terms of soil and water contamination that could be caused by these conventional energy systems. So we're looking at potential contamination by petroleum hydrocarbon, heavy metals, and other toxic chemicals that could be released through these conventional energy production systems. Waste materials such as the sulfur stacks that are a waste material as a byproduct of the oil sands energy production system. And so those waste material have to be dealt with, such as the petroleum coke as another example of waste material that would have to be dealt with. And in Northern Alberta, again, in the oil sands, more than 1 trillion liters of OSPW, oil sands process affected water in the tailings ponds in Northern Alberta. It's obviously a really big eyesore to many people, and those are some of the environmental impacts that we would have to be dealing with as well. A lot of these conventional energy would, during their production, during their storage, during their transportation, there's a risk for spillage. For example, in the United States, spillage from tanker accidents amounts to about 60 per year. And also in the US, about more than 1 million liters of petroleum is spilled into the coastal waters. And so again, those amounts to a huge environmental impact. In the Canadian soil, such accidents such as spillage and contamination of the soil and water, you would frequently occur as well. This is back in 2013, but if you pay attention to the news, these spillage would occur very, very frequent, right? We have derailment quite often occur. Another form of contamination is these soil and water contaminations through these petroleum storage tanks. A lot of them may leak and causing large number of sites, contaminated sites. So this is the number, you'd be looking at thousands. So this is a news article which published a few days ago, February the 16th, 2022, accusing the Alberta government hiding some of the contamination problems, contaminated sites. But I don't necessarily think this article is, that the government is necessarily hiding these numbers. Those numbers are available on the internet and so forth. But the key is the key message here is that the number of sites are really large, and this also points to the scale of the problem that we are facing in the province. Moving on to talk about the impact on the air. Okay, checking on my time. So these conventional energy system, for one thing, the production of these energies themselves can be quite energy intensive. For example, in the oil sands, as an example, the greenhouse gas emissions, this is based on 2013 data, makes up 8.7% of the entire greenhouse gas emissions in the country. So this obviously is fairly highly significant. The oil sands operations on an annual basis emits about 70 million tons of CO2 on an annual basis. The other point, I think, in terms of climate change, as far as the climate change is concerned, is that these conventional energy all emits carbon dioxide or greenhouse gases through the combustion of those fossil fuels. Right, so the combination of annual fossil CO2 emissions, coal, hopefully with the restrictions on the usage of coal, or many developed countries restricting the use of coal as an energy source, this emission is going to be decreasing. But oil and gas emissions of carbon dioxide, carbon emissions from burning of oil and gas obviously are going to be continued unless we replace them with alternative energy sources. Another impact of the conventional energy systems on the air is obviously emission of pollutants. Here the example is emission of ammonia in the oil sands. So really obvious that where the oil sands operations are really intensive, the emission, the ammonia concentration in the air is very high. And these type of nitrogen and sulfur emissions from energy production systems would enter into the atmosphere and eventually would be coming down in the form of acid deposition or nitrogen and sulfur deposition. Okay, and these acidic deposition would then cause soil acidification. This is the data coming from Alberta. Long-term soil acidification monitoring, we're seeing a reduction in the soil pH caused by acid deposition going from the 1980s all the way to the 2000s. Okay, so this again illustrates the impact of the conventional energy production systems on the air quality on the air. Moving on to talk about the effect on the biota. Obviously, the disturbance, the surface disturbance I mentioned earlier, is going to damage the ecosystem, removing the vegetation and cause damage to the soil, fauna, etc. as well. Exposure of the biota, such as animals and human beings, to the polluted air, water, and soil, obviously will be causing significant influences on the biota. Okay, fossil fuel combustion is going to cause a lot of pollutants, particulate matter as another example where it's going to pollute the air and influence human health. So the discussion so far has been focusing on each of those ecosystem components or environmental components individually. But if I could use the global biogeochemical cycle of vanadium as an example, it's really clear that the influence of these conventional energy production systems on the soil, water, air, and the biota is really well connected. So we really have to think about them as an integrated system. We can't really separate the impact on these different components individually. Everything is connected, and we have to really evaluate them as a system. And I know I have used up my time. The I have 2 more slides to really quickly go through. So why, you might be asking, why are we still using these conventional energy? There are a few points we have to consider. That conventional energy obviously has its own advantages. They may be cheaper to use. We have the technologies to use them, and by convention, right? The second thing is that emission intensity has been decreasing. So we are improving our technology. We are using new methods to extract the conventional energy resources to cause less disturbance. We are developing clean air technologies. We are trying carbon capture and storage to reduce our impact. But regardless, alternative energy sources are obviously urgently needed. In terms of some of the disturbances, we are developing reclamation techniques to deal with that. And Danny is obviously going to come back to talk about this in a lot more detail. And my last slide, as a really quick summary, the use of conventional energy comes obviously with a really large environmental cost. Some of the environmental impacts can be mitigated, however, and more sustainable energy sources will replace conventional energy in the long run. This is what I believe, and this is obviously what we are looking forward to. Thank you.
Thank you, Professor Chang. Particularly the end there is a great transition into our second speaker, Dr. Amalesh Dhar. So Dr. Dhar is going to speak about renewable and sustainable energy sources. He's, as I said, a research associate here at the University of Alberta in the Department of Renewable Resources. And he works on reclamation and restoration research projects that include understanding the environmental impacts of wind, solar, and geothermal energy systems. He obtained a PhD from the University of Natural Resources and Life Sciences in Vienna, Austria, and has over 10 years of experience in various research fields related to natural resources management at universities including British Columbia, the University of Northern British Columbia, and the Bulkley Valley Research Center. And with that, I will pass it to Dr. Dhar.
Hello, everyone, and thanks, Dan, for introduction, and thanks everyone for listening my talk. And Professor Dr. Chang provide valuable information about the conventional impact, environmental impact of conventional energy system. Now, in this presentation, I will discuss renewable energy systems, solar, wind, and geothermal, their importance and potential environmental impact. Before going into more details, let's have a look what is the potential of renewable energy system. Based on the figure in the right side, it shows that renewable energy sources have the potential to provide 3,078 times the current global energy need, of which solar energy is providing the highest amount, 50 times, whereas wind energy 200 times and geothermal energy 5 times. If we look at from this times to the number digit, it shows that the solar energy can produce 6.5 million gigawatt of electricity, whereas wind can produce 1.7 million gigawatt of energy. As of production, as of 2020, total 90% of the global electricity is coming from the different renewable sources, of which the solar, wind, and geothermal are contributing to around 10% of this energy. So from this, and now it comes to why renewable energy is important. If we look at and compare the greenhouse gas emission between renewable energy and conventional energy system, then we can see that in the left side, this is the greenhouse gas, carbon dioxide, and then compare with the renewable energy and conventional energy. The solar, wind, and geothermal has a very less amount of carbon dioxide compared to conventional energy systems such as coal, oil, and gas. Similarly, sulfur dioxide, nitrous oxide, this also way less than the or near zero for the renewable energy compared to the conventional energy system. Therefore, it comes to move from carbon intensive energy to renewable energy system can help us to mitigate the climate change that we are facing nowadays. with a different extreme environmental situation and safeguard the energy security for the future, as we see that it's an enormous amount of energies out there, and increase the sustainability of the human activities. For example, in USA, if solar energy contributes 10% of the national demand, then reduction of carbon emission would be 6.5% to 18.8%. So this and now it comes to see that in terms of world prospect, what is the status of Canada in renewable energy? Canada is 9th in solar energy production and 8th in wind energy production, and we have a very less amount of geothermal that's mostly used for the heating purpose. And in the right figure showing that the change of or progress of solar and wind energy system from 2005 to 2017. And first geothermal plant is about to establish in Saskatchewan. That is will power around 5,000 homes, and it can offset 27,000 ton carbon dioxide per year. So from the Canadian prospect, let's have a look to the Alberta. What is the status of Alberta in terms of renewable energy? Solar energy in Alberta currently have 0.1 gigawatt, and that can offset almost 50,000 carbon dioxide equivalents. And by 2025, this solar energy production will be 1.8 gigawatt. Wind energy currently 1.8 gigawatt, or 9% of the total energy supply in Alberta, and third in Canada, and 6.5 gigawatt would be in by 2025. Geothermal energy, we are in the very beginning stage, and 3 plant is approved with approximately 36 megawatt. So this is the overall picture of the geothermal, renewable energy system. And now it comes to that everybody thinks the renewable energy is clean and it doesn't have any impact. So the question is, are solar, wind, geothermal energy as clean as widely believed? Let's have a look. Before going into detail, just give a brief how the solar panel works. In this figure, if you look at the sun, we get the sunlight, and then the solar panel use the sunlight and produce electricity and transfer to the home inverter and then use the electricity. And if the house producing more electricity, then some of the electricity can transfer to the grid, and less electricity then comes from grid to the house. And this is the way solar energy is working. So now what is the possible environmental impact we are getting from the solar energy system? Due to the construction of the solar farm, so major cause is soil compaction. So using the equipments and all this can causes the soil compaction, and cleaning the vegetation on the topsoil. Because of the construction, then topsoil erosion occurred, and due to topsoil erosion, increase the sedimentation and turbidity in the local stream. Then water. The dust is the dust deposition on the solar panel decrease the amount of solar radiation absorption. That's therefore it needs to clean. So 860 liter per megawatt hour is required to clean the mirror and panel of panels dust, and up to 90% of the water used by the this energy system are using for dust cleaning. Then comes to the emission. For generally in operation stage, solar panel is not emitting any emission, but during construction or manufacturing, panel manufacturing, it produce 14 to 18 gram per kilowatt hour carbon dioxide and 0.1 gram per gigawatt hour mercury it can emit, as well as there's some emission during the construction and the transportation stage. Then environmental impact. So obviously any kind of disturbance on the land, its vegetation loss will occur. And the most important factor for the solar energy is the wildlife mortality. From the different study in USA, it shows that 37 to 138,000 birds killed by the solar solar energy system per year. And as well as habitat loss and fragmentation because of the big area required to establish the farm. So it loses the habitat, especially for endangered species if there is something, or create a landscape fragmentation. As well as when the farm is established, there need to be make a boundary, and therefore it create a barrier for the wildlife movement. The footprint, generally a solar farm requires a bit higher footprint than the any other energy system, but over the long term period, if we consider the life cycle around 25 to 30 years, it requires less amount of footprint, and it's estimated that 8.69 to 56.3 meter square per kilowatt. As well as it conflict with other land use system like agricultural land, forest land, or other land where it established. So always there is some conflict about the with the land. Then hazardous waste. So solar panel generally to prepare solar panel required the chemical compound cadmium, selenium, and lead. So cadmium used as a semiconductor to convert the solar energy to electrical energy, and it requires 5 grams of cadmium per meter square of solar panel manufacturer. And this cadmium is highly toxic, and potential exposure to cadmium dust and vapor can be a carcinogenic. Then comes to the wind energy system. So again, similarly, just to give a brief how the wind energy works. So wind blow past turbine and rotates the blade. The kinetic energy is transformed into the mechanical energy, and a gearbox spins the generator to produce electricity, and then this electricity go to transformer and to the grid. So this is the way is wind energy work in a brief. So if we consider the environmental impact for this wind energy, the most important one is the visual issue. That's the change the natural landscape view. When you see the long big tower, wind tower on the landscape, some people is not like it, but it depends on the perception of the different people. Some people like, some people does not. So it's depends on the people perception, as well as NIMBY syndrome, that is called not in my backyard syndrome. And in that case, some people don't like to see the wind turbine in their backyard or near house. And another impact is shadow flickering. When the turbine blade is rotating, then sunlight reflecting on the blade, and it can causes this shadow flickering, and that's the very annoying during the driving or is far from the house, or shadow flickering. Then vegetation and wildlife. So for vegetation, habitat loss, wildlife movement, that's the similar like I explained to in a solar energy system. So all disturbance have some form of impact on habitat loss and wildlife movement and various. As similarly in wildlife mortality, especially for bird, the yearly it was killed 2,000 to 34,000 birds killed by the wind turbine in USA. And if we look at this, the figure on the right side, so that's the if we compare this figure, still any other mortality, that's wind energy is way below. If we compare with the conventional energy system, then fossil fuel power plant had a more than 14 million bird mortality per year in USA, compared to if we compare with the solar and wind energy system. Then the another is noise. So what happened when wind turbine, the blade is moving, it creates a irritating rhythmical swishing tone that is though less than 1000 hertz, but So continuous this kind of noise is create some annoying, and then it's sometimes it's a bit difficult to tolerate. So that's create this kind of noise. And then the local climate. From the research, it find out that when wind move across the blade of a wind turbine, the existing wind loses significant amount of momentum, which disturb the natural exchange of energy between the land surface and the atmospheric layer, and that may alter the local hydrometeorology. And as well as and some study find out that it increased the temperature. So based on a study in the US, it shows that global temperature could increase 1 centigrade by 2100 if 1% of the energy come from wind energy source. Then the footprint. Generally, wind turbine requires less footprint. For permanently, it's less than 0.4 hectare per megawatt. But and temporary, it requires 1.5 hectare per megawatt because of the construction and the movement and all these activities. It's require more land, as well as it's also create a conflict with the other land use to where to put that on agricultural land or forest land and so on. Then the geothermal energy. The geothermal energy that comes from the ground, power extracted from heat stored in the earth. So if we look at the earth, the different color is indicating the different temperature. And so if you go inner side, that's temperature high, 5000. As you go up, its temperature start to decreasing. So for geothermal energy, temperature is required around 120 centigrade. But if temperature is higher, it provides better energy system, better geothermal and electric production. So if we consider how this system works, then if you look at this figure, that's the cool water going underground and then heat exchange and then come hot stream, and there's a generating the electricity, and again it's go down the circulating. That's the way this energy is producing. The possible environmental impact from the geothermal energy is the compaction, as I already explained to this one, and physical and chemical properties because of the making that big wells to extract the energy from the ground, and soil contamination by mercury or boron, and this kind mercury, boron, as well as air emission, greenhouse and toxic gas emission occurred. But it's this kind of contamination is fully depends on the stream chemical composition, meteorological condition, and resource temperature, and it can vary from location to location. And the water and contamination of aquifer and other water bodies can be contaminated if leakage through the wells. And to establish a well, 2-kilometer well requires 8,000 to 55,000 cubic meter of water. And vegetation and wildlife, as any kind of disturbance, obviously deforestation, habitat and ecosystem loss can occur through this energy system. And another important part is the geophysical and land hazard, that is subsidence. So generally 1 to 55 centimeter per year subsidence can occur through the geothermal energy system. In addition, landslide and hydrometeorological eruption can occur. The footprint, it requires very little amount of footprint, just like a well. So it's 0.02 to 3 hectare per megawatt hour, as well as conflict with other land uses. And the take-home message from solar, wind, and geothermal energy, I'm almost over my time. These energy systems are not free of adverse environmental consequences and have low greenhouse gas emission and land use, and all are abundant in nature. And the major environmental drawbacks are bird mortality for solar and wind, biodiversity and habitat loss for all trees, noise for wind, visual impact, especially wind, hazardous chemicals, solar and geothermal energies. And geothermal energy has a small risk of subsidence, induced seismicity and landslide, which potentially serious consequence can occur if it's happened. And if you are interested to more read about that, the 2 papers we published. And thank you.
Well, thank you very much, Dr. Dhar. That's wonderful. And so in the first two talks here, we've had a nice overview of the impacts of first conventional energy systems with Professor Chang, and now conventional energy systems. So we're going to move on to how to address these impacts and how to mitigate them before they even happen. So for that, we'd like to invite the third speaker, Dr. Danny Degenhardt. She's a reclamation scientist with the Canadian Forest Service. She's also an adjunct professor here at the University of Alberta in Renewable Resources. She received a bachelor's in chemistry from the University of Alberta and master's and PhDs from the Soil Science Department at the University of Saskatchewan. Currently, she's working with a team of multidisciplinary researchers to develop reclamation techniques and technologies to accelerate the creation of sustainable forest ecosystems after industrial disturbances. And so with that, I would invite Dr. Degenhardt to give her presentation.
Okay, awesome. Thank you for the invite. So I'm here to talk about reclamation and mitigation to some extent. I'm going to focus my talk on the reclamation side on the oil sands, since that's what I know most about. I will start off with the mineable oil sands and then move on to the in situ side. So there are currently 8 active surface oil sand mines operating in northern Alberta under 4 different companies: Suncor, Syncrude, Canadian Natural, and Imperial. All of them uses the same extraction process. I'll just give you a quick primer. These are open pit mines. They use truck and shovel to excavate the bituminous sand, which then are transported to an extraction plant where the bitumen is separated from the sand using the Clark hot water extraction process. Just a tidbit, that process was invented back in 1929 by Dr. Carl Clark, who was a scientist with Alberta Research Council. And now Alberta Research Council, or InnoTech Alberta, is located on Carl Clark Road, just south of the city here. Anyways, so in 2020, mined bitumen accounted for about 50% of the total bitumen production in Alberta. As a byproduct of bitumen extraction, we get tailings and oil sand processed water, as alluded to by Dr. Scott Chang's presentation. Tailings are a mixture of sand, clay, silt, water, residual bitumen, and other hydrocarbons, salt, and trace metals. Oil sand processed water, or OSPW, are essentially the free water in tailings ponds that contains less than 5% solid. OSPW has the same chemical profile as the tailings. In addition, it also contains dissolved organic components such as naphthenic acids, phenols, and PAHs. Tailing ponds act kind of like a holding area in which water can be removed and recycled for continuous extraction. And it also acts as a settling basin to separate the water from the tailings. So they can be out of pit, like the one in this diagram, or an in-pit structure, like the one in this picture. So the issue with tailings is that it's going to continually grow as extraction continues in the province. As of 2020, there's about 1.36 billion meters cubes of total fluid tailings. The tailing ponds cover an area of 257 kilometers square. That's about roughly twice the size of Red Deer. Like I mentioned, the growth is expected until 2030 at about 1.7 billion meter cube, at which time that's the end of mine life for Syncrude. And this equates to about 680,000 Olympic-sized swimming pools. So this diagram on the right kind of highlights the production of tailings on a volume basis for each of the mines. So what is the objective for reclaiming tailings and oil sand processed water? Well, the tailings is managed under the framework, the tailings management framework, which stipulates that any new fluid tailings from a project must be ready to reclaim 10 years after the end of mine life. whereas all the legacy tailings must be ready to reclaim by the end of mine life. So fluid tailings are considered ready to reclaim when they've been processed with an acceptable technology, placed in their final landscape position, and meet the performance criteria developed based on that deposit. Generally speaking, ready to reclaim tailings will be integrated into one of two different types of closure landforms. End-pit lake, like the one on your top right, or a terrestrial landform, like the one on the bottom right. Basemine Lake in Syncrude is one of the first end-pit lake commissioned about 10 years ago. It's roughly about 800 hectare in size, contains about 45 meter fluid tailings capped with 5 meters of water. All oil sand companies have proposed end-pit lake in their mine closure plans, but it's still currently too early to know if end-pit lake is an effective reclamation strategy for tailings, which means the other option is to cap tailings with sand or overburden material to create terrestrial landform, and then in order to do that, to place a cap on the tailings, the deposits have to be trafficable. And that's a huge challenge. How do you consolidate tailings to make them trafficable? Generally speaking, you require some type of active treatment and time. Some of the treatment technologies that are currently used by companies include adding polymers or some kind of coagulants to enhance clay flocculation, some type of co-deposition, mixing fluid tailings with sodic overburden, or centrifugation. On this table here, you'll see that multiple treatment technologies are utilized at each mine. There's still currently a lot of uncertainties in terms of treatment efficacy and deposit performance over time. There's a lot that we don't know about how polymers may degrade over time and whether or not that deposit will stay cohesive. There's still a lot of research required in terms of capping these deposits. How do we do it? What materials we use, and whether or not these deposits are able to support target ecosites. Moving on to oil sand process water. So currently, all companies are under a zero discharge practice, and it has been since the mine first started. That means no water is released under this practice, and currently there is no water release criteria or policy in place. In this article on your right, as alluded to, published by CBC back in December 2021, this water release criteria is coming. The companies are moving towards treatment, and mainly to target reduction in toxicity associated with naphthenic acids. Treatment ranges from using very high energy active technologies traditionally used in water treatment plants, adding coagulants, sedimentation, filtration to adsorption and oxidation, all the way to the spectrum of passive low energy nature-based solutions such as constructed treatment wetlands. Moving on to the in situ oil sands. 80% of Alberta's oil sand deposits are actually too deep for open pit mining. So instead, they're extracted in situ using SAGD, or steam assisted gravity drainage. So there are currently 31 active SAGD projects in the province, accounting for about 38% of the total bitumen production. Again, a quick primer on the whole SAGD process. It involves drilling a pair of 1 kilometer long horizontal well, one that sits about 5 meters on top of the other. Water, which usually are saline, are heated to become steam, and then it travels through pipeline and injected into the upper well. The steam heats up the bitumen, allows it to flow by gravity into the producing well below, and the result oil and condensed steam emulsion is then piped from the producing well to the plant nearby, which then is separated and treated. Generally, the produced water is recycled to generate new steam. again, it's a very energy intensive process. It requires about 2.6 barrel of steam for every barrel of bitumen produced. In addition to that, seismic lines are created to locate bitumen deposits. So this is probably the largest disturbance from in situ oil sand mining. So seismic lines, for those of you who don't know, are these narrow clearings cut through the forest to provide access for seismic exploration equipment, like I said, to use to locate bitumen deposits. Companies are not required to reclaim seismic lines. And so since the 1950s to the early 2000s, these conventional seismic lines ranging from 5 to 10 meter in width are cut all across the province. Recovery on these seismic lines are very slow and inconsistent. Typically, these disturbances from decades of exploration activity are still persisting on the landscape today, as you can see in the pictures. And on the diagram on your right is a photo from ABMI showing the extensive footprint of seismic line on Alberta's landscape. In some areas, seismic lines can reach a density up to 40 kilometers per kilometer square. So what are the impacts of seismic lines? Like I mentioned, trees reestablish very slowly on seismic lines due to various reasons such as compaction, competition, low light availability, and repeated line use. And there's also issues with topography and terrain wetness, and also creates environmental impacts on permafrost, hydrology, and carbon storage. And one of the bigger impact of seismic line is the large-scale fragmentation of the landscape, which have found to affect wildlife habitat use and predator-prey dynamics. We know through research that seismic line facilitates the movement of wolves, resulting in an increased predation of the threatened woodland caribou. So as Dr. Chang mentioned, there's about 1.8 million kilometers of seismic lines in Alberta, and about 250,000 of those are within caribou ranges. So how do we restore a seismic line? And does it even work? The government of Alberta actually drafted this framework to kind of guide the restoration of legacy seismic lines, I think back in 2018. And it's mostly focused on caribou habitats with the overarching goal of stabilizing and recovering the caribou population. This framework suggests applying restoration treatments such as site prep, mounding, ripping, tree planting, and the use of woody material to create microsites, as well as to reduce access. There's also more and more forestry companies, including seismic lines, as part of their reforestation plans. So when they harvest from a cut block, they will include a lot of the seismic lines nearby in their restoration or reforestation plan. But seismic line restoration is not cheap and it's not easy. It costs about $10,000 per kilometer. It's also hard to know if it's effective. Just because you plant a tree on the seismic line, it doesn't mean it's going to grow. And to mitigate the impact of seismic lines, the province has offered a financial incentive to companies to reduce the width of seismic lines. So the 2D seismic lines, or the conventional seismic lines, which range from 5 to 10 meters width, were phased out in the early 2000s, and replaced them with the 3D or the 4D seismic lines. They're slightly narrower, ranging from 1 to 1.5 meter in width. So there's less disturbance on the landscape using these new technologies. And as well, the province came out with a draft woodland caribou range plan, which aims to achieve 65% undisturbed habitat in the caribou ranges. So they've invested money to create 1.6 million hectares of new provincial parks, as well as investing in $85 million to restore seismic lines in the caribou habitat. Most oil sand companies are motivated to reduce their greenhouse gas emissions for one reason or another. And one of them is the Technology Innovation Emission Reduction Regulation, which regulates large emitters to reduce their greenhouse gas emission intensity by 10% compared to their average emission between 2016 to 2018. So for a lot of these vertically integrated oil sand companies that have assets both in the mineable and the in situ oil sands, it's easy to find greenhouse gas mitigation solutions in both the midstream and the downstream process. So the diagram on the left is actually from Suncor, and that's their greenhouse gas emission reduction target, and it highlights how they're going to achieve that. And the figure on your right is actually from CNRL, or Canadian Natural, discussing how they plan to reduce their greenhouse gas emission. Again, a lot of these solutions comes from their midstream, downstream process and not a whole lot from the upstream process. So I think that's all I have today for you. Thanks.
Great. Thank you, Danny. So we'll head into the final talk, which is by Dr. Sylvia Sleep. So Dr. Sleep is an assistant professor in civil engineering at the University of Calgary. She received a PhD in civil and mineral engineering at the University of Toronto. And prior to starting her faculty position in Calgary, she completed an ICE High postdoctoral fellowship in chemical and petroleum engineering at the University of Calgary, where she focused on systems levels assessment of carbon capture and utilization technologies. Her current research interests center on the development of methods to assess the life cycle, environmental and economic implications of new technologies to aid in decision-making under uncertainty. And today she's going to discuss the life cycle assessment of energy systems. So welcome, Dr. Sleep.
Okay, I hope everyone can see that. So other presenters today have been really speaking about the environmental impacts of different energy systems and the different reclamation options. I'm going to change gears a little bit in this talk to really focus on how we assess the impacts of our activities and specifically look at a couple of examples from the energy industry. But before that, I just wanted to get started by giving some context about the current discourse around the climate impacts of energy and the role that LCA can play in this context. So many governments and different companies around the world, including energy companies, have committed over the last couple of years to achieving net zero greenhouse gas emissions by 2050. And this was really motivated by a 2018 special report by the Intergovernmental Panel on Climate Change, which said that to keep global warming below 1.5 degrees Celsius, we would need to reach net zero greenhouse gas emissions by 2050, or by 2090 to keep warming below 2 degrees Celsius. And so on the figure here, you can see the trajectory that we have been on is that yellow line in terms of our global greenhouse gas emissions in gigatons per year. And so to meet that 2-degree warming, we would need to start following the red line. And so that includes both massive investments in GHG mitigation technologies. So that's making up that green component of the chart. But then also, because there's some emissions that are just not feasible to decarbonize or eliminate completely, will also require the investment in carbon removal technologies to get to that net zero. And so when we say a net zero system, we're often thinking only about direct or combustion greenhouse gas emissions. So something like an electric vehicle might be net zero on site, but it isn't net zero when you consider the full supply chain. And so to get true net zero, you need to include both those scope 1, 2, and 3 emissions, and think about the whole system within which your technology is operating. And so that would also include scope 2 emissions, so the indirect emissions from electricity supply, as well as scope 3 emissions, which includes the upstream and downstream supply chains and end of life of your product. If we look at Canada's greenhouse gas emissions, in 2018, Canada emitted 728 megatons of CO2 equivalent. And if you look at the breakdown by sector, you can see that electricity was only 9% of the emissions of our national emissions. And the majority of our emissions actually come from transportation, oil and gas, and the building sectors. And so within those greenhouse gas emissions in the other sectors, some of those emissions are non-energy related. So things like material or the embodied carbon, embodied emissions in cement, for instance, and building materials. But a lot of them are related to the non-electricity energy consumption in those sectors. So on the right, you can see the energy demand by fuel for Canada in 2018. And you can see that electricity is actually only 17% of the total energy demand in 2018. And that the majority of that energy demand was actually met by refined petroleum products, so things like gasoline and diesel, and natural gas. And decarbonizing, getting to net zero, will require that we address the greenhouse gas emissions, not just from our electricity supply, but also from how our demand for fossil fuels, as well as those embodied emissions. And that's complicated because getting to a net zero electricity grid is just really not far enough to meet those targets. But we can't just today eliminate all fossil fuels because we don't have the infrastructure in place to provide zero greenhouse gas emissions energy to our different sectors. And so to do that would require a lot of investment in infrastructure redesign and new technologies. But the question then is, what do we know would do, what changes should we make to get the biggest benefit? And where should we prioritize our changes to meet our decarbonization targets? And that's where life cycle assessment comes in. So understanding how to make this transition requires a systems perspective. So it means not just looking at that direct emissions or the direct site, but taking a step back to look at the whole system and the interaction between the system and other systems in the environment. Life cycle assessment is a systems tool. So it's one means for doing a systems analysis. And it assesses the environmental burdens of a process, product, or system over its full life cycle, what we call from cradle to grave. And so you can see an example of a cradle to grave on the right here. And so that's considering from material extraction through manufacturing, transportation, the actual use phase of the material or product, and then through to disposal or recycling. And so life cycle assessment, the first LCA was conducted in 1969 by Coca-Cola. And they were looking at trying to figure out what would have lower environmental impacts, glass or plastic bottles. Over the next 20 years or so, there were a lot of product focused life cycle assessments that did those types of comparisons. So a common example would be something like comparing plastic, disposable to reusable cloth bags to paper bags. And there was a lot of questions around the results and recommendations coming out of these life cycle assessment studies and concerns about the robustness of the methods employed and the kinds of assumptions that were being made to draw those conclusions. And so to address those concerns, in 1977, the International Organization for Standardization published the ISO 14040 guidelines. And these are a framework, provide a framework for life cycle assessment with the objective to increase the consistency, transparency, and robustness of life cycle results, to help give the public and readers of LCA studies more confidence in the results and recommendations coming out of those studies. If we look at the ISO framework itself, it's a 4-phase framework on the left, and it starts with something called goal and scope definition. And this helps you look at framing your study to say, why do you want to do this study? So what's important? What question are you trying to answer? And then how are you going to scope the study? To do that, you have to define your system boundary. So say which activities will be included or excluded from your system. You need to think about the temporal scope. So whether you're looking at a study about something happening today or into the future. And then it's also defining a functional unit. And so if you see life cycle assessment results, they're often presented, say for electricity, you would be looking at per greenhouse gas emissions per kilowatt hour of electricity delivered. And the functional unit provides a consistent metric or measure so that you can compare different product systems on a common basis. After goal and scope is the inventory analysis. And this is where you would go out and actually collect the data about each different operation within your system to get the process unit mass and energy flows. And you would use that to build out your system. And then you would start modeling the inputs and outputs from the system by multiplying those energy flows by emissions factors. So things like the carbon intensity of the electricity supply. The next phase is the impact assessment, and that's where you take the individual flows from the inventory analysis and you relate them to a final emission or environmental impact of the system to give you something that you can actually evaluate and use to make comparisons. And then the last stage, it's an iterative process, but the last sort of step after each phase is interpretation. This is where you look at your results and you think, what kind of conclusions can I actually make from this study? And is there anything missing from the study, or are there any uncertainties or areas where I should go back to maybe the goal and scope or the inventory, revise my research question, or collect more data, say, to help give me more confidence in the answer. Going back to the evolution of life cycle assessment, after the standard was passed in 1997, the biggest change in the next 20 years, or so the last 20 years of LCA, has been the use of LCA in policy, and particularly in energy policy development. The most notable of these was the California Air and Resources Board, which in 2007 enacted the low carbon fuel standard. And the standard was the first standard to actually embed life cycle assessment results in policy. And so the standard was enacted in 2007. It began in 2011, and it set a goal of a 10% reduction in the carbon intensity of transportation fuels sold in California by 2020, a 20% reduction in the life cycle carbon intensity of the fuel mix sold in California by 2030. And so what that actually meant was that each fuel supplier needed to know the life cycle carbon intensity of their fuel. And so this fuel standard meant that overall, for the full fuel mix, they needed to achieve a carbon intensity reduction. And so they weren't picking, say, winners of different technologies. They were saying, however you can achieve that reduction, so whether by reducing the carbon intensity of your existing pathway, blending in other lower carbon fuels, or purchasing offset credits from other suppliers, you need to use one of those methods or all of those methods to meet your reduction targets. And so what that's looked like from 2011, by 2020, there was a 7.5 reduction in the carbon intensity of the fuel. And they're on track to meet that 20% reduction by 2030. Since the enactment of this policy, similar policies have been enacted all over the world, and Canada has a national clean fuel standard that is being adopted. So outside of low carbon fuel standards, how else can LCA help in the energy industry? It can help inform decision making. So if you were designing a product, you could say which aspect of my product's life cycle has the biggest impact on the environment and why. So would that be driving a car, building a car, or fueling a car? And then you can, from that, understand what you should focus on to reduce your environmental impacts. It can also be used to inform policy. So looking at the greenhouse gas emissions implications of wider use of biomass in fuels and plastic. You can answer a question like if CO2 enhanced oil recovery helps or hurts the climate on a net systems basis, or what the implications of electric vehicle adoption would be within a specific power grid. LCA more recently is also being used to assess new technologies. And so this is the focus of my research. And essentially when we're looking at new technologies, we can divide them into two different types. There's technologies that are new, that haven't been deployed in any market, so that would be an emerging technology. There's also commercial technologies that haven't been deployed before that would, you could look at the implications of deploying them in a new market. And so the types of research questions that we would ask are things like how you can adapt life cycle assessment to better assess emerging technologies where the system isn't actually exist yet. You can look at how LCA can better inform the development of early stage technologies. So getting like from the lab scale in and helping to inform that development. Some of the work that I've been doing lately is around carbon capture, utilization and storage, and also different hydrogen applications. And so that concludes my presentation. Yeah, so basically life cycle assessment is a tool that can be used to assess those trade-offs. It is really critical at this point in time because of the scale of transformations that are required in our economies. And it can be really useful in terms of product selection, policy, and technology development. And that concludes my presentation. So I'll turn it back over to the hosts.
Well, thank you, Sylvia, and thank you to all the speakers for the excellent presentations this afternoon, and in particular for giving our audience an overview of the environmental impacts of energy systems and how to assess and address those impacts. So we've learned today a few things from the four speakers. We started with Scott Chang, and he discussed how the conventional energy systems cause soil and land disturbances, the connections of these disturbances with the stability of soil carbon, and ultimately that links to global climate change. We discussed soil and water contamination with hydrocarbons, metals, and other waste materials, the atmospheric impacts such as greenhouse gases and acid deposition, and ultimately how the sum of these impacts biota that includes humans. Amalesh had the second presentation. He discussed renewable energy sources, including solar, wind, and geothermal, both now and the potential of these systems in the future. We gained an understanding of how renewable energy systems impact the landscape, both during the manufacturing of items such as solar panels, and all the way to later impacts during use to soil, to water, and even to wildlife. And we learned of some landscape and societal issues as well, such as the visual appearance of these structures, solar panels and wind towers, noise, and even changes in local weather conditions. Danny brought the conversation together, discussing reclamation and mitigation by giving some examples of conventional systems, including bitumen extraction, both open pit mines and SAGD, and the processing impacts in Alberta. And then went right into a discussion of reclamation strategies and technical challenges in both the reclamation of the mines themselves and treating the oil sands processed water that comes out of these pits. Concluding with a final example of touching back on Professor Chang's discussion of seismic lines, the impacts of those on the landscape, to permafrost soils, again to wildlife, and strategies to mitigate those disturbances going forward. And then we heard the fourth speaker, Sylvia Sleep, open with a discussion of the role of net zero greenhouse gas targets by governments, target out at 2050, how we actually assess what net zero means from an upstream to downstream components of an energy system, including the embodied carbon, the need for new infrastructure here and in other places to actually provide net zero energy to society, which would require significant resources and investment. And finally, a nice discussion of what an LCA is, a life cycle assessment, how one is developed, and a discussion of how they're a way to look at a whole system, how they interact with other energy systems, and ultimately to the environment. So really a cradle to grave approach. We will now transition into an open discussion panel in the remaining, I guess, 15 minutes or so that we have. Please remember to add your questions into the Q&A and include the name of the speaker to which you are directing your question. And so I think we have quite a few questions queued up, actually. I'm going to bring those over. And I'll start by asking the panelists to please, show themselves and unmute if you don't mind. I think the 5 of us will be safe in doing that. So I'll open with a broad question, and I guess we can pass it around, maybe directing it to Sylvia first. So the question is this, and I'll read here. With systems thinking, we want to address the full effect of our energy, not just extraction or generation. We heard that conventional energy sources have significantly higher greenhouse gas emissions, but when we think about the environmental impact of energy sources, whether they be alternative or conventional in terms of pollution, the footprint, reclamation, or life cycle assessments, what are our biggest concerns, I guess, when we construct a life cycle assessment?
Yeah, so I think in thinking about those broad scale transformations of our energy systems, we really need to be taking that full systems perspective to understand what the potential unintended risks or consequences are of those transformations. And so something that if you're just looking at the direct system might not have a hugely negative impact, but when you're expanding it to the scale of like replacing all of our fossil energy with renewables, you need to start looking at what the possible unintended consequences are of those huge, massive shifts to our supply chains.
Great, thank you. Maybe to Scott or Amalesh, how do you define the magnitude of the disturbance that might be caused by a particular energy system, whether that be conventional or renewable? Perhaps starting with Scott.
Okay, I guess there are many different ways to measure that. Like if you're looking at greenhouse gas emissions, you quantify the amount of greenhouse gas being emitted. You can compare that among different energy production systems, compare between conventional versus renewable, as Amalesh has done. So there are different ways to quantify that. And you can quantify the amount of area that was disturbed. You can quantify the degree of the disturbance. So different disturbance obviously will require different assessment as to the degree of disturbance.
Sounds good. Amalesh, in the renewable space, what do you have some insights on this? In particular, those energy systems are a little bit different. Thinking about the scale of the impact, you discussed solar and wind, which have considerable footprints on the landscape, and also maybe the duration of the impacts of these energy systems as you deploy them on the landscape.
Actually, it's depends on the target or prospect of the energy system. For example, if you go for solar energy system, so what is the target? It's for only one time up to 25 years, because this the life cycle for one set of solar and panel is around 25 to 30 years or something this range. So in that point of view, if you look at all the point, it's clearly shows that the overall impact from the all three renewable energy system is very low compared to the conventional energy system. But and then the impact what we found, it's if we want to mitigate those factors, still we have some tools and the process already out there that can applicable to reduce those environmental impact and all this part. So
Thank you. That's a perfect segue. I'm actually going to pass it to Danny with that. So just I guess a general question, whether it be conventional or unconventional, we have a land disturbance that's caused by one of these energy systems. In your line of work, what kind of things do you look at to define the magnitude or the sort of effort or energy or cost, financial costs that would go into reclaiming a landscape?
I think that is broadly almost dictated by the regulations, because it goes back to what do you want to reclaim it back to and what are the regs. And certainly I think in Alberta we do have some of the strictest regulations when it comes to reclamation standards. So I think, yeah, the cost and the effort that you put into reclamation will be largely defined by the policies and the standards. Yeah.
Do you have thoughts on well, I guess what's the definition of reclaimed? I know this gets tossed around a lot, and at least 3 of you are in renewable resources. So I'm curious how you define reclaimed, and I'd add to that, if you want to chat about it, who should get to define what it is? Is that the government or the university or some sort of sharing? I guess that's a bit of a softer question, but it's one of the speakers is audience members is curious about it.
That's a good question. I think the definition of reclaimed or reclamation, I guess recovery or whatever you want to call it, it's all defined by the policies that dictates the outcome. So, and right now it's the Alberta Energy Regulator. They enforce the regs, and the policymakers from Alberta Environment makes up the regulations, and the energy regulator will enforce it. So they do seek input from researchers and the scientific community, but largely it's driven by a lot of these policymakers.
And I guess to add to that, in Alberta, we have the so-called, I guess it was mentioning on one of the slides that I presented, that you need to get the reclamation certificate. I think that's the stamp where it says you are fully reclaimed. But the caveat there is also that if there's any problem develops down the road, even though you have the reclamation certificate, if there's problem developing down the road, like contaminations still occurring, seepage water that's still toxic and so forth, you still have to address them. That you can't really walk away from that site.
Right. Sylvia, are these things weighted in LCA analyses then? Is there a way of including the regulatory regime in which you're operating in a particular energy system?
Yeah, well, I think you would be looking at the potential, like modeling the impacts of your current activities. So that would account for whatever that regulatory system is. I think in terms of looking at impacts outside of greenhouse gas emissions, it can be a lot more complicated to do in an LCA, and there is progress being made there, but definitely still the focus is on greenhouse gas emissions specifically.
Okay, well, thanks for that. We're getting close here, so I'm going to pass around one big picture question to everybody. Let's start with Amalesh, I guess. The order isn't too important, but curious what you think the greatest challenges facing energy systems in the environment today, and what can be done about it.
Challenge is actually, it's also depends on what types of energy we are using. Let's say if we consider the conventional energy system, then we have the potential problem is that that include the air pollution, that's I already mentioned. Then that will directly link with the climate change, water pollution, thermal pollution, solid waste disposal. And this emission of air pollutant from fossil fuel combustion is the major cause for an urban area pollution too. So, and therefore, and from conventional energy to, if we move to the renewable energy, So as we are always talking about the benefits of renewable energy, but still it has some limitations. The example is the availability. One of the biggest concern is the power generation depend on natural resource that we cannot control it. Like if we put the solar panel and then we don't have enough sunlight, then we cannot produce the solar energy. Or wind turbine, we cannot get that on. So it's beyond our human human control. And the information barrier, still many people are not easily accepting this energy, especially for the renewable energy system. And because of the lack of information or the awareness of the people, or another thing is what's the benefit and also, and so we need to reach to the people to convince them if they wanted to the renewable energy. That's the one part. And another part is the cost issue. For example, if you want to go solar energy in your home, so you have to spend in a lot of money. And if you go for geothermal, especially for heating, that's also cost a lot of money. So, and therefore many people are not interested with those this renewable energy system at the beginning. So this is the challenge I'm seeing for the both the conventional energy or renewable energy related. Yeah.
Great, thank you, Amalesh. Scott, biggest challenge facing energy systems and the environment. What are your thoughts on that?
Well, I guess I don't really have a lot more to add. I fully agree with what Amalesh has already said. It's really the environmental impact. You know, if we can find or develop an energy system that has really little or no environmental impact, then obviously that would be a silver bullet for the society, right? And secondly, the cost. If any new technology, if it's not sustainable economically, everyone has to survive economically as well, then that technology likely is not going to survive. So I think both in terms of its environmental impact as well as its economic viability, I think those are the two biggest challenges that we will be facing.
Great, thank you, Scott. I'll pass to Danny. Your thoughts about challenges in developing sustainable energy going forward.
I guess part of it is progress and investment. I feel like in a way we're not making enough progress right now in terms of reclamation. And I'll speak to just reclamation, especially in the oil sands. And partly because it's still an active mine. So reclamation, especially progressive reclamation, is happening probably a lot slower than we like to see. And we know that it takes a long time for trees to grow. So, so to get to the end goal of having a sustainable ecosystem in the future to hand over to our kids, I don't know if it's achievable if we don't start right now. And we probably should have started this 20 years ago. So, yeah.
Thank you. And Sylvia, I guess your thoughts from the life cycle assessment perspective and what our challenges are going forward.
Yeah, I think just the biggest challenge would be the scale and speed of transformation that would be required to meet our net zero targets, and understanding that the full systems perspective implications of those changes.
Well, thank you. And thank you again to all of our speakers for sharing your expertise and your time today with the audience. We hope that you all have the audience has enjoyed today's session. And again, we encourage you to sign up for future webinars. There'll be 2 more this semester. If you're here, please fill out the survey with your feedback. It's really valuable to our team as we develop future webinars. If you're interested in catching up on past sessions or rewatching today, the webinars will be posted again on the Future Energy Systems YouTube channel and the Energy System website fairly soon. An announcement then that our next session, the 4th one of these webinars, will be coming up on March 8th at 3 p.m. And in that one, we'll discuss the ethics and the politics of energy systems. For more information on that session and to keep up to date with many of the energy research developments here at the University of Alberta, you can sign up for the Future Energy Systems newsletter. Once again, thank you to all the speakers, to the audience for joining us today, and we look forward to seeing you again soon. Take care.